Welcome, everybody, to what I expect is going to be the last one of our long-form class meetings where we spend most of the time talking about new material for the semester. The goal for today is going to be to wrap up just the last couple of topics for the semester, which both have to do with trigonometry. So the topics we'll be going through today are going to see us first getting an introduction to the reciprocal trigonometric functions. So for all the sine, cosine, and tangent that we're already familiar with, each one of those has an alter ego that we get just by taking its reciprocal. And for historical reasons, those functions have different names than the originals. So because often when you're doing trigonometry, especially in the service of doing geometry or algebra, it's convenient to talk about the reciprocals of trigonometric functions, and so we'll meet those today as functions in their own right. And then we'll take an opportunity to work through what are called trigonometric identities. What trigonometric identities are they're equations that relate together the various trigonometric functions with one another. So, for example, if you tell me what the sine of an angle is, I should be able to tell you what the cosine of that angle is without doing a particularly whole lot of geometry. We can do it just using algebra because, among other things, we have an identity that relates together the sine of an angle and the cosine of that same angle. And all of these identities arise out of the corresponding geometry. So all we really need to know in order to discover these identities is we need to know just the basics of right triangle trigonometry and geometry. And not surprisingly, the Pythagorean Theorem plays a central role in that whole thing. So we're gonna meet the Pythagorean identity for trigonometry, as well as the addition formulas for sine and cosine. And then we'll extend those to the double angle formulas for the same as well. So that's how we're going to spend our time today. If you're taking my class this semester, what the plan is for the next 2 weeks going forward, now that we're sort of wrapping up the new material for the course, is we're going to be spending our time on assessments. So the quizzes and the exams for the semester will be available to you to work on, to submit, to receive feedback on. Our web work problem sets remain open for you to continue working in the course, so don't forget to stay engaged with those as well. And we're just going to use it to just really kind of get caught up, get back up to speed, answer your questions about your performance in the course up to this point, take stock of what learning topics that you've mastered and which ones are still going to need some more work on for the semester, and get ready for sort of wrapping things up as this strange pandemic semester wraps up. So let's get started. Let's take a quick look at the agenda that I have in mind for today. So the first thing that we want to do is meet the reciprocals of the trig functions. So we know sine, cosine, and tangent. Sine, cosine, and tangent are our fundamental trigonometric functions. And each one of those has a corresponding, I call it an alter ego, a function which is the reciprocal of it. So for example, associated with the tangent of an angle, the tangent function, its reciprocal is a function called the cotangent. And when I say reciprocal, I want to write that word over here in the margin to remind us that that's really what these arrows that I'm drawing represent. Reciprocal just means that when I multiply those two quantities together, if I multiply those two functions together, the result is going to be the constant number 1. Or another way to say that is that by definition, the cotangent of any angle, the cotangent of an angle alpha, is nothing more than the reciprocal 1 over the tangent of that angle. That's all we mean by reciprocal. Right? So for example, if you tell me that the tangent of an angle is 3 over 7, then I can tell you that the cotangent of that same angle will be 7 over 3. That's all there is to it. It's just a definition that's motivated by nothing more than arithmetic and some historical force of geometry behind it that made it convenient to give these reciprocal functions their own names. But don't be fooled. You already know all the properties of these functions because they are just the original trig functions flipped upside down, 1 over the original trig functions. And in that same construction, and this is one that trips up students. Every trigonometry student ever gets tripped up by this at least once. The sine function has a reciprocal as well. And the name of the reciprocal to the sine function is cosecant. That's unfortunate, but we are kind of stuck with this. There are a variety of reasons why the reciprocal of the sine function ends up getting that co-designation. One of them that you'll see in calculus comes from the fact that the rates of change of the reciprocal of the sine function are actually opposite. They're negative when we would otherwise have expected them to be positive. And so it gets that co-function just because the minus sign pops up when you look at its rates of change. So the reciprocal of sine is cosecant, or cosecant, however you want to pronounce that. And then the last one of these three, the reciprocal of the cosine function, is what we call the secant. So there are three pairs of reciprocals. The cosecant is the reciprocal of the sine, the secant is the reciprocal of the cosine, and the cotangent is the reciprocal of the tangent. So that's all there is definitionally to know about these reciprocal functions. So let's take a look at this activity out of Bolkin's active prelude to calculus and see how we can use these ideas of the reciprocal trigonometric functions. So in this problem, we're considering a right triangle, and we know the length of its hypotenuse is 61, and the length of one of its legs is 11. So we know two lengths of the sides in this right triangle. Let's try and sketch it out. Kind of plausibly, but probably not really. I'm not sure if this diagram is to scale. So here is a right triangle. We're given that the hypotenuse has a length of 61. So that's this side. And one of its legs will have a length of 11. By the way, I know that that's got to be the shorter of the two legs, only because if I had 11 and something less than 11, if I squared them and added them together, the result would be less than twice 11 squared, which is 242. So it's not going to be as big as 61 squared, which is in excess of 400. So for sure, 11 is the shorter leg. That's just, it's not a perfect diagram to scale, but at least we know 11 is going to be the shorter leg in this triangle. Okay, let alpha be the angle that's opposite the side that has length 11. So here's my side of length 11. I'm just going to go opposite to the other side of the triangle, and that's where I'm going to find the angle that I label alpha. Okay, so what we're being asked to do in this problem is, first of all, to find the exact length of the other leg. So this missing third side in my right triangle, find out what its length is. And then once I know what its length is, I should be able to use right triangle trigonometry to just go through and figure out the lengths of all the rest of the remaining sides as well. Once I know that, I can have all of the values of these trigonometric ratios, everything from sine, cosine, and tangent, which we already knew several weeks ago. And then also now we're going to know how to find secant, cosecant, and cotangent, because they're just the reciprocals of the ones that we already knew how to find weeks ago. So we'll be able to use SOHCAHTOA, but we can't use SOHCAHTOA until we know the length of that third side. So I'm going to move this over for just a second until we have resolved this question. How do I know what is the missing length? Well, the only information we have is the length of the other two sides in my right triangle. And for that reason, we know that the Pythagorean Theorem is what we can use, because the Pythagorean Theorem is what relates together the three lengths of the sides of any right triangle. So if I call this missing length, let me not call it A, because that looks too much like the angle alpha. Let me call it B. If I call that missing length B, then the Pythagorean Theorem tells me that B squared plus the length of the other leg, 11 squared, is going to equal the length of the hypotenuse, 61 squared. So there's my Pythagorean Theorem. I just have to solve this equation now for B. Well, 11 squared is otherwise known as 121. 61 squared, I don't know off the top of my head, but I'll just ask a calculator how to do that. 61 times 61. That would be 3,721. So that's pretty large. 3721. And so if I'm trying to get that B by itself, my next step is going to be to unwrap it from the addition by 121 by subtracting 121 from both sides. Subtract 121 from both sides, I'm going to get 3,600 on the right-hand side. And oh, look at that. That's a number that actually has a pretty friendly square root. If I take the square root of both sides, I'm going to find out that B is going to be plus or minus the square root of 3,600. But of course, the square root of 3,600 is otherwise known as 60. And since B is a length of a side of a Euclidean right triangle, we know that its length is not going to be a negative number. And so we'll just take the positive value, B equals 60. So now we have the length of our third side. And that equips us to answer any question at all about the trigonometric functions, the trigonometric ratios associated with any of the angles inside my right triangle. Let's take them one at a time. First, the ordinary trig ratios that we already knew several weeks ago that come out of SOHCAHTOA. Right? SOHCAHTOA is the mnemonic that reminds us that the sine of an angle is the ratio of its opposite side divided by the hypotenuse in that triangle. And so, if I'm trying to find out the sine of this alpha, I should be taking the ratio of the opposite side, which in this example is 11, divided by the hypotenuse, which is 61. So the sine of alpha is going to be the number 11 over 61. And there's that. But now I'm going to pause for a moment, and let's use that information to figure out what is the reciprocal. The reciprocal of sine is otherwise known as cosecant. And therefore, we can use the fact that we now know the sine of alpha to instantly compute the cosecant of alpha. It's just the reciprocal, 1 over the sine. And since my sine is already a ratio, it has a numerator and a denominator, right? The reciprocal is what we get just by flipping the numerator with the denominator. So the secant of alpha, the cosecant of alpha, see, I told you it'd screw you up because it screws me up still. The cosecant is the reciprocal of sine. So if the sine is 11 over 61, the cosecant is 61 over 11. So as soon as you find one of these trig ratios, you can right away find its reciprocal. So once you know the sine, you instantly know the cosecant. If we take that same logic to find the cosine, according to SOHCAHTOA, cosine is the ratio of adjacent to hypotenuse. The adjacent side here is 60, the hypotenuse is 61, and so the cosine is going to have a value of 60 over 61. And therefore, its reciprocal, which we call the secant, is going to have the value that is the reciprocal of that ratio. Instead of 60 over 61, the cosecant is going to be, the secant is going to be 61 over 60. Nothing to it, right? Now all we have to do is figure out the tangent, which according to SOHCAHTOA is the ratio of the opposite to the adjacent side. And so the tangent of my angle alpha is going to be the ratio of 11, the length of the opposite side, divided by 60, which is the length of the adjacent side. And so immediately we can say that the cotangent, which is the reciprocal of the tangent, is going to be the ratio with numerator and denominator reversed, 60 over 11. And so that's all there is definitionally to what secant, cosecant, and cotangent are. So this is definitely not something to be overthought today. We just got introduced by name to 3 new functions, but these 3 new functions are just defined quite simply in terms of functions that we already knew. The secant is the reciprocal of the cosine, the cosecant is the reciprocal of the sine, and the cotangent is the reciprocal of the tangent. And so since these functions are reciprocals of the functions that we already knew, one of the ways of thinking about what their graphs, so as a function we can think about what the graphs of these functions look like. We can understand those, for example. I like this illustration from our textbook, our Active Prelude to Calculus textbook. This is an illustration of the graph of the secant function, f of t equals secant of t. I'm going to just expand that a little bit. And one thing that I notice about this graph is that really it looks like everywhere that the cosine, so the cosine is the blue dotted graph that we're seeing here in the middle, everywhere that the cosine was equal to plus or minus 1, the secant also was equal to plus or minus 1. The graphs are touching at those points. Why? Because 1 and negative 1 are in fact the only 2 numbers that are equal to their own reciprocals. If I take the reciprocal of 1, I get 1. If I take the reciprocal of negative 1, I get negative 1. And so the graphs touch at that point. But that's the only place that they touch. And everywhere else, the value of secant of t is greater than 1, so up here, or less than negative 1, the parts that are down here. Right? Why? Because when we take the reciprocal, we are turning the axis inside out. We talked about this a little bit last week when we were talking about rational functions. So just imagine we started with a cosine function, but then we took the y-axis and we just sort of broke it apart here at the origin, and we flipped it outwards, just everted it, turned it inside out. So that everything that used to be close to 0 is now way out towards infinity, and everything which was way out towards infinity is now down close to 0. Well, cosine only oscillates between positive and negative 1 to begin with, so it never got close to infinity at all. But it did get close to 0. It got close to 0 a lot of times. And everywhere that the cosine got close to 0, for example, right here at x equals pi over 2, everywhere that the cosine gets close to 0, the secant, its reciprocal, blows up. Right? Because when we turn the y-axis inside out, everything that used to be close to 0 is now way out towards plus or minus infinity. And so the secant function is going to have vertical asymptotes everywhere that the cosine function was equal to 0. Because everywhere that a function is equal to 0, its reciprocal will blow up towards plus or minus infinity. For the same reasons we talked about in Monday's video about rational functions, right? These vertical asymptotes are arising for the same reasons that the vertical asymptotes of our rational functions did in our last video. So everywhere that the cosine was 0, every odd integer multiple of pi over 2, the secant is undefined and its graph reaches a vertical asymptote. Everywhere that the cosine was equal to plus or minus 1, so was the secant equal to plus or minus 1. And everywhere else, the value of the secant is bigger than 1 in absolute value, because the value of its reciprocal, the cosine, is smaller than 1 in absolute value. And so picture the same phenomenon happening for the sine and the cosecant, which are also reciprocals of one another, just shifted by pi over 2 units. Right? Everywhere that sine is equal to 0, which are now the integer multiples of pi, the cosecant is going to have a vertical asymptote for the same reason that where cosine has zeros, secant has vertical asymptotes. And then for the cotangent, you can imagine that we have a similar story. Sorry, let me hide this table of contents for a second so we can see the whole thing. This is the graph of our original tangent function, right? Ordinary tangent that we already met a while back. And so what would we imagine is happening for cotangent? Well, everywhere that the tangent is 0, so every integer multiple of pi, once again, everywhere the tangent is 0, we're going to expect there to be a vertical asymptote for the cotangent function. Everywhere that the tangent function has a vertical asymptote because it's blowing up to plus or minus infinity, we're going to expect that the cotangent is going to be close to 0. In fact, it's going to cross the 0 point at those points. So what you might imagine, and let's actually do this in a graph here. Let me pull up a graphing tool. So here's my tangent function. I'm going to get the grapher here to label my axis using pi's, as we are accustomed to. Let's have this. Yeah, I think that'll do it. Okay, so here is a graph for my ordinary tangent function. And now what's going to happen if I take the reciprocal, g of t equals 1 over f of t? Here is my cotangent function. So notice what my cotangent function is doing. I'm going to make my tangent function a little bit less prominent here so we can make sure we're seeing what we need to see. So my original tangent function is now the dotted green lines. My cotangent function, let's actually put the label on the graph here. Show the label with the name and the value. There we go. So this is my cotangent, otherwise known as 1 over tangent. And my cotangent function has a vertical asymptote everywhere that my original tangent function had an x-intercept. All right? Everywhere the tangent was close to 0, cotangent, its reciprocal, is going to be close to infinity. In other words, blowing up to plus or minus infinity. And conversely, everywhere that my tangent function got close to infinity, blew up to a vertical asymptote, my cotangent function is getting close to 0. So it has its x-intercepts at pi over 2, 3 pi over 2, 5 pi over 2, negative 1 pi over 2, and so forth. Okay, so those are some of the basic properties that the graphs of these reciprocal functions have as well. We're going to keep these reciprocal functions in mind as we start talking more today about important trigonometric identities and the processes of solving trigonometric equations. Let's make that pivot now. So I think one of the, if you've taken a course on trigonometry that was a more intensive course. So our pre-calculus and trig course that we're in this semester, we don't really get the luxury of taking a deep dive into trigonometry. We get just enough of it that we can do a lot of the fundamental things that we need to do. But entire semester courses on trigonometry are out there, sometimes in high school, sometimes in college. And one of the things that those courses often do to just sort of kill time, quite obviously, is they really take deep dives into the algebra of trigonometric functions. And that comes in two forms. One of them is in solving trigonometric equations, so solving for an unknown angle inside of a sine, cosine, or a tangent. And the other is in developing and proving trigonometric identities. And that's the business that we're going to talk about today. Because these identities provide us with fundamental relationships among the trigonometric functions. So among sine, cosine, tangent, and their reciprocals, secant, cosecant, and cotangent. So what are trigonometric identities? What do they look like, and what can they possibly do for us? The first one that I want to dwell on, and it's got to be the most fundamental of them all. I like to say that if you're kind of stranded on a desert island and you need a trig identity at some point, chances are the one that you can figure it out from is called the Pythagorean identity. So that's going to be the first one that we look at. And like its name suggests, the Pythagorean identity is nothing more than a warmed over version of the Pythagorean theorem from geometry. Here's how. So we know, for example, the Pythagorean theorem tells me that in any right triangle, the sum of the squares of the lengths of its two legs, so a squared and b squared, if I add those together, is equal to the square of the length of its hypotenuse, c squared. So you learn that right away as soon as you learn anything about right triangles. We know how to relate the three lengths of those sides together. On the other hand, SOHCAHTOA gives me definitions for the sine and the cosine of an angle inside of a triangle in terms of ratios of two sides in that same right triangle. So the sine of this angle that I've labeled theta here is the ratio of its opposite side, b, divided by its hypotenuse, c. So sine of theta is b over c. Similarly, cosine is the ratio of the adjacent side, a, to the hypotenuse, which is c. And so at the end of the day, we can take these two pieces of data, these two pieces of information, one of them coming from classical geometry, the Pythagorean theorem, relating the three lengths of sides together. And I can take, on the other hand, my right triangle trigonometric definitions that tell me what sine theta and cosine theta mean in terms of ratios of two lengths of sides. We can smush them together and discover that, in fact, sine theta and cosine theta are mutually related one to another for any angle theta that we could choose. So here's how the algebra works in order to make that discovery. We start with the Pythagorean theorem, a squared plus b squared equals c squared. And I would ask, all right, how do I get something in this equation to look more like something that SOHCAHTOA tells me about? I want to know something about how b over c and a over c relate, and not just how a and b relate to c. So an option that I have is just to take this Pythagorean theorem equation and just divide both sides of it by c squared. So I'll do that by writing this as 1 over c to the minus 2, then multiplying both sides by c to the minus 2. And multiplying by c to the minus 2 is the same as dividing by c squared. And what I get is an equation that looks something like this, right? I've got now a squared over c squared plus b squared over c squared is equal to 1. Well, since both numerator and denominator are squared, we can factor those squares out, can't we? Using familiar, friendly properties of exponents. Just factor that square out. And once I've done that, now I have revealed a ratio a over c and a ratio b over c inside of this equation. And that's really good news because those are exactly the ratios that I care about. Those are the ratios that we call sine of theta and cosine of theta. So why don't we take this cosine equation and let's get the a by itself. I'm just going to multiply both sides by c. Now I have the a by itself and I can substitute that a into this a over here, c times the cosine of theta. And when I take c times the cosine of theta and divide it by c, the c's cancel. And oh look, we've got the square of the cosine of theta, or what we call cosine of theta quantity squared. So now I've gotten my cosine of theta into this equation. Same story for my b over c. If I solve this equation for b is equal to c times the sine of theta. And then I'll just substitute c times the sine of theta in for that b. But when I do that, c times the sine of theta is being divided by c. And so those c's can be reduced to give me sine of theta, the quantity squared. And so at the end of this process, we now have eliminated all the a's, b's, and c's from this equation down here on the bottom. And the result is what we call the Pythagorean identity in trigonometry. The Pythagorean identity is the identity cosine squared of theta plus sine squared of theta is equal to 1. In other words, if you tell me what the cosine of a certain angle is, right, then that value squared plus the square of the sine of that same angle is always equal to 1 no matter what angle theta is. So how might we put this into practice? Let me go back to my whiteboard here for a moment. So suppose that I happen to know, this is a classic Pythagorean identity type of problem. Suppose that I know that the cosine of some angle, let's call it theta, let's suppose that I know that it's equal to 5 over 12. And so the question I would ask is, what is, not theta, but what is the sine of theta? So this is a classic example, right? We now have a relationship between cosine and sine of theta given by this Pythagorean identity. And so we should be able to use this Pythagorean identity. If I know what the cosine of an angle is, I can use it to determine the sine. So let me write the Pythagorean identity down here. So according to the derivation that we did, cosine squared of theta, which, by the way, that's just another way to write the cosine of theta, the quantity squared. That's another piece of notation that is kind of historically significant, but can be not that illuminating to us early on as we're still getting used to all this stuff. So this is a Pythagorean identity. It came from the Pythagorean Theorem, as we just saw. So now that I know that the cosine of theta is 5 over 12, I just want to take and use that knowledge. Cosine theta is 5 over 12. I'll just substitute that value in here for the cosine of theta. And so I'll put in here 5/12, the quantity squared, plus the sine of theta, which is this thing that I don't know, squared, is equal to 1. And now all I have to do is to solve this equation for the sine of theta. If I can get sine of theta by itself, then I have finished with this problem. And the sine of theta that's unknown is sitting right there. So we'll just do what we always do and solve this equation. Let's simplify 5 over 12 squared. Multiply it out. It's 25 over 144. Plus my unknown sine of theta squared is equal to 1. Let's subtract 25 over 144 from both sides. Sine of theta, the quantity squared, is 1 minus 25 over 144. And so I'll do 144 minus 25 up here in the numerator. 144 minus 25 is 119. Yes, over 144. And so that's the square of the sine of theta. So now to find out what the sine of theta is, I'll take the square root on both sides. And remember, when we take the square root on both sides, we end up needing to worry about the sign, S-I-G-N, of the answer, right? It could be positive, it could be negative, and unless we have a good reason, we can't rule either one of those out just yet. So we'll take and do the square root of 119 over 144. And we can simplify that radical if we want to. 119 is actually, it's a multiple of 7, isn't it? But is otherwise not divisible by a perfect square, right? 119 is 7 times 17, if I have that right. Yeah, 7 times 17. But there's no perfect square in there, so the best that we can do as far as simplifying it is just by calling it the square root of 119. Meanwhile, 144 is a perfect square. It's just the square of the number 12. And so the sine of theta is plus or minus the square root of 119 over 12. So that actually gives us more than one potential answer to this question, right? But that's okay, actually, because let's think about geometrically on the unit circle. What are we really asking in this problem? If I have my unit circle down here, centered at the origin, has a radius of 1, Here's my unit circle. Remember that on my unit circle, the cosine of theta describes the x-coordinate. Sorry, let me write this in a different place because I'm going to have to use this unit circle. The cosine of theta describes my x-coordinate, and the sine of theta describes my y-coordinate. And so if I happen to know that the cosine of an angle theta is equal to 5 over 12, that means that at 5 over 12, which is a little bit less than 1/2, right? It's right here, 5 over 12. That is the x-coordinate of the point on the unit circle that we're interested in, right? But the x-coordinate of 5 over 12 describes for me more than one place, more than one location on the unit circle. It describes for me this point right here, which is in the first quadrant, and it also describes for me this point down here, which is in the fourth quadrant. And either one of those two is an answer to what angle theta gives me a cosine equal to 5 over 12. And so from that viewpoint, now we know there's two possible angles theta on the unit circle that meet this description. And those two angles happen to have different, in fact, opposite signs. They have opposite signs because their signs have opposite sign to one another. One of them is positive, the other one is negative, but they are otherwise the same in absolute value. So this square root of 119 over 12, that's the y-coordinate, or at least that's how far away from the x-axis that this point on the unit circle is going to be. And so one of those values is here on the positive side, square root of 119 over 12, the positive version. And the other one is down here on the negative side, negative the square root of 119 over 12. So from that perspective, you know, it makes sense that there's more than one possible answer to this question. Because if all you tell me is the cosine of the angle, that doesn't tell me whether my angle is in the first quadrant or in the fourth quadrant, because both of those are the quadrants in which the cosine of their angles is positive. But in one of those quadrants, the sine is also positive, namely the first quadrant, and in the other one, the sine is negative, namely the fourth quadrant. But without getting lost in those details, the most important ingredient in the work that we just did is this Pythagorean identity, right? The relationship between the cosine of an angle and the sine of that same angle, in that the sum of their squares is always equal to 1, regardless of the angle that we put in there. This is most helpful in any algebra problem, and as you get into calculus, it's useful in calculus problems as an algebraic sleight of hand. Anytime what you have in a formula is a sine, and what you'd like to have is a cosine, or vice versa. If you're stuck with a cosine and you want a sine there instead, all you need to do is rearrange this identity to get you the thing that you want. So what do I mean? Let's suppose that I'm stuck with cosine in a formula, and I'd like to have sine instead. Well, what I can do is just subtract sine squared theta from both sides of this identity. And now that I've done that, I can take the square root on both sides to find out that I can just replace anytime I have anytime I have a cosine and I'd rather have it written in terms of sines instead, I can rewrite cosine as the square root of 1 minus sine squared, with again this plus or minus sign ambiguity that we just saw in the last example. And the very same thing could also be done if I'm stuck with sine and I'd like cosine instead. Just subtract the cosine squared from both sides, and then take the square root on both sides, and sine likewise can be replaced by the square root of 1 minus cosine. So this Pythagorean identity is the most fundamental and important of any trigonometric identity that you will ever learn. You can derive so many other salient trigonometric algebraic facts using just this identity and some clever algebraic manipulation, so don't sell it short. Of course, now that we know the Pythagorean identity for sine and cosine, and we've also been introduced to their reciprocals, the cosecant, the cotangent, and the secant, that should mean, and I think it does mean, that we also can have some identities that involve those reciprocal functions as well. Let's imagine, for example, what might happen if I don't know, took my cosine squared and I just wanted to divide both sides of the Pythagorean identity by this cosine squared. So if I did that, I'm going to have something that looks like this. How do I get this to, I want to make that negative exponent, I want to make it positive. I know there's a way. Well, okay, so let's pause here for just a second. we can multiply this into my fraction just by putting it up here. So let's take a look at what we have up here on the screen. I've got sine squared over cosine squared. I can factor that square out. And in the middle here, I have sine of x divided by cosine of x. Well, what is sine of x divided by cosine of x? I think my graspable math system here doesn't know the answer to that, so we have to supply the answer to that. That's just the tangent. So the left-hand side of my equation here is nothing more than 1 plus tangent squared of x. So that's what I have over on the left. Meanwhile, on the right-hand side, cosine to the power minus 2. We can see that instead as the reciprocal of cosine squared. But what's the reciprocal of cosine squared? 1 over cosine of x squared. So that's really, what I'm looking at on the right-hand side over here. Oops, I'm sorry. Don't want to confuse things here. That's 1 over cosine squared. 1 over cosine squared of x. There we go. That's what I wanted. But again, that square that's down in the denominator, we can take this and combine it with a secret square on top of that 1. We can factor this square out. And if I factor this square out, we can write it as 1 over cosine, the quantity squared. 1 over cosine of x, the quantity squared. But we know another name for 1 over cosine. The name that we know for 1 over cosine is we're calling it secant. Right? And so what we end up with here at the end, once we've done the simplifications, once we've put in the other names that we know these trigonometric functions by, we get 1 plus the tangent squared of x is equal to the secant squared of x. I don't know why my x got lost there for a second. We should probably put it back in. There. Clumsy, but at least now we can see this identity the way that it would otherwise look. Okay. So this is another face on the Pythagorean identity. All we had to do on the original Pythagorean identity is just divide the whole thing through by cosine squared. And what we're able to then do is get a new Pythagorean identity that instead of relating sine to cosine, now it relates tangent to secant. And this one is super duper useful. You could imagine doing the whole same process, just instead of dividing by cosine squared in the beginning, if we instead divided by sine squared in the beginning, move this to this side, and then we'll turn this negative exponent into a positive exponent, multiply the cosine squared into the numerator, factor out the squares, and now take a look at what we have this time. Right. This time I've got on the left-hand side cosine of x divided by sine of x. And so where tangent was sine over cosine, its reciprocal, cotangent, is cosine over sine. So what I have is the cotangent squared of x. That's what I have as my first term over here on the left-hand side. Right? That's what that simplifies to. And in the meantime, sine to the minus 2 of x, that's 1 over sine squared, which is the same as the reciprocal of sine squared. But the reciprocal of sine is cosecant. And so my right-hand side is cosecant squared of x. And so if we take stock of everything, the right-hand side of this equation is cotangent squared of x plus 1. And the right-hand side is cosecant squared of x. And that becomes yet another face of the Pythagorean identity. So, in other words, what these things are useful for is if I have one trig function and I want to rewrite in terms of another. The original Pythagorean theorem lets me exchange sines for cosines, or vice versa. The first reciprocal version that we did a minute ago lets me exchange tangents for secants. And this version lets me exchange cotangents for cosecants. And so super useful across the entire algebraic enterprise of trigonometry, these different faces on the Pythagorean identity and the Pythagorean theorem. So what I'd like to do with this is I'd like to begin a little bit. Let's put this into at least some preliminary practice using another exercise. This one again comes out of Bulkin's Active Prelude to Calculus. So here we're given a right triangle that has a hypotenuse of 1 and a vertical leg of x. So let me sketch that to get us started, and then we'll go from there. So here is my right triangle. We're given that it has a vertical leg equal to x, so let's put that x over here on this vertical leg. The hypotenuse is 1, so I'll put a 1 over here on the longest side of this right triangle. And the job for us is to determine the simplest expression that we can for each of the following things. Let's do one of the ones that we can do fairly quickly. I actually want to start with the cosecant of theta. So to figure out the cosecant of theta, well, remember that the cosecant of theta is nothing more than the reciprocal of the sine. So cosecant is 1 over the sine of theta. Right? And therefore, the cosecant is going to be the opposite ratio from the sine. The sine is the opposite over the hypotenuse, and so the cosecant is the hypotenuse over the opposite. The length of the hypotenuse divided by the length of the opposite side. And so theta, I forgot to draw this in the question, right? Theta is the angle that's opposite the x, right? So the hypotenuse is 1. The opposite side to theta has length x. And so the cosecant of theta is going to have the length 1 over x. So now that I know what the cosecant of theta is, let's take this opportunity to let's apply one of these Pythagorean identities. Let's use this one that we just derived, right? This one is going to let me interchange cosecant, which I know now, with cotangent. So if I were asked, I'm going to put in here a fictitious part g. If I were asked to determine the cotangent with just the information that I have, the cotangent of theta, well, we can use this identity. We might just have to rearrange it a little bit. Right? I want to get this identity's cotangent to be by itself. And so to do that, let's subtract 1 from both sides. And then let's take the square root of both sides. And I think it's not going to let me do this. I'll just put it in the line underneath it. So if I take the square root on both sides, I'm going to find out that the cotangent of x is equal to plus or minus the square root. I guess I can have a button for square root here. The square root of cosecant squared of x minus 1, all underneath the radical. So there's the secret plus or minus in here that I didn't write, just this once. So the cotangent is the square root of the cosecant squared minus 1. So coming back to our problem, we can use that. I'm going to put the plus or minus back in, because I don't want to forget that. It's plus or minus the square root of cosecant squared of theta minus 1, with all of that under the radical. But we know what the cosecant of theta is. The cosecant of theta is 1 over x. So I'll substitute 1 over x into this expression. Plus or minus the square root of 1 over x. And then that needs to be squared, minus 1. And there's an expression for the cotangent of theta. We could continue to simplify this if we were interested. It's good practice with manipulation of rational expressions. We would get something like 1 minus x squared over x squared underneath the radical here. And when I took the square root, I would get something like square root of 1 minus x squared, all divided by x. Again, with that plus or minus doing some heavy lifting out there in the front. So again, the point of this exercise was just again to give us an opportunity to apply the Pythagorean identity, to exchange in this example the cosecant that we knew for the cotangent that we didn't know. Okay, let's do one more example of one of the parts on this, and then we'll talk about one more family of trigonometric identities before we wrap up today. I want to do, well, let's do part F here first. In part F, we're being asked for the cotangent of the arc sine of x. So we got kind of two things going on at the same time, and one of them is an inverse trigonometric function, right? The arc sine of x. So I want to convince you that we already know how to do this problem. In fact, we already have done this problem. Let's think first about what the arc sine of x is. What does it actually mean? Well, the arc sine of x remember, arc just means inverse in terms of inverse function. So arc sine of x is the inverse function of the sine function. So if the arc sine of x is equal to some angle, let me call that angle alpha, right? Then if we interchange the roles of x and alpha, we are interchanging the function, the arc sine function, for its inverse function. And its inverse function, so we're kind of turning this function inside out, kind of replacing it with its inverse. The inverse function, I'm sorry, I'm writing off the screen one more time. Let me just go back to this view. If we exchange the x with the alpha, we are exchanging this function for its inverse function. But its inverse function is called the sine function by definition of arc sine. And when I interchange the alpha with the x, I find out that the sine of alpha is equal to x. Right? Okay, so the arc sine of x is an angle, alpha, whose sine is equal to x. But in fact, if we had done part A here, we would have found out that the sine of theta is in fact equal to the opposite over the hypotenuse, which is x divided by 1, which is equal to x. So secretly, this alpha that I'm talking about is nothing more than just the theta from my triangle in here. Right? So alpha is just another name for theta in this problem. And so what I mean by that at the end of the day, my Zoom meeting just ended. Let me just restart it here real quick. Sorry about that. If you're watching this video, you have no idea what just happened, but my Zoom meeting was idle for 40 minutes, and so it timed itself out. That's okay. We're all still here. Okay, so arc sine of theta is nothing more than just x. And so, sorry, arc sine of x is nothing more than theta. And so this question is just asking me for what is the cotangent of theta. And we already found that. It's the square root of 1 minus x squared divided by x, with potentially a plus or minus sign sitting out in the front. We may be able to resolve this question about the plus or minus sign, by the way, because would we expect for an angle theta inside of a right triangle to have a positive cotangent or a negative cotangent? Well, since cotangent and tangent are just reciprocals, they're going to have the same sign, SIGN, as one another. So if the tangent is positive, so is the cotangent. If the tangent is negative, so is the cotangent. But the tangent of an angle in a right triangle is nothing more than the ratio of opposite divided by adjacent. By the way, the length of this adjacent side, according to the Pythagorean theorem, is the square root of 1 minus x squared. And so the tangent is going to be x divided by the square root of 1 minus x squared. And so the tangent is definitely positive, and therefore the cotangent is also positive. So our caution about the sign ambiguity here, well, it's always a good idea. We can actually resolve it in this example because my angle theta is a first quadrant angle. So its tangent is positive and therefore its cotangent is also positive. Okay. So let's use this opportunity to pivot to our last set of trigonometric identities that we're going to meet. So ultimately the identity that I want us to reach for is called the double angle identity. And what the double angle identity allows me to do is, for example, it allows me to say what is the sine of twice an angle. How can I write the sine of twice an angle, the sine of 2x? How can I write that in terms of the sine of x itself? So that's the big question when we ask about a double angle identity. So we want one for sine, and we also want one for cosine, if we can find it. So we're going to take kind of a roundabout approach to finding these double angle formulas, but they're all going to be informed by geometry. So the first thing that I want to do is I'm going to draw a diagram, and we're going to mine this diagram for as much information as we can. And once we have all the information that we need about this diagram, we're going to know everything that we need in order to make our conclusions about the double angle formula for sine as well as double angle formula for cosine. So let's take a look just at the diagram here. I want to expand out my screen so we're just seeing the diagram I want to see in the beginning here. Okay. Great. So let me give you a tour. So here I have a diagram, and it has a couple of different, well, it has a lot of different things going on. The first thing that I did is I drew a right triangle here inside of my unit circle. So this is my unit circle. It's got a radius of 1. This point here, A, is the center of my unit circle. And I drew one point out here on the circumference of my unit circle. So it's 1 unit of distance away from A. And then between the x-axis, or rising from the x-axis, I'll draw out one angle that I'm going to call x. And then starting from x, I'm going to draw out one more angle that's called y. Okay, so this angle here is the angle I'm calling x. This angle here is the angle I'm calling y. And one thing that we notice is if we go from the x-axis all the way out to this ray, AD, that angle is going to be x plus y in measurement. Right? So this whole angle here, EAD, that angle would be a measure of x plus y. And then what do? Well, I extended this radius all the way out to the edge of my circle. Then I'm going to drop a vertical down to the x-axis. So that what I have here is a right triangle, AED. Its hypotenuse is equal to 1, and this angle over here is the angle that measures x plus y. So there's one important right triangle for the work that we're about to do. But then also, I'm going to, from the point out here at D, I'm going to drop what we call an altitude. I'm going to drop this segment here, DF, that makes a right angle with this ray emanating from A at an angle of x with the x-axis. Right? So DF is perpendicular to AF, and so we have a second right triangle, AFD. And one of the acute angles in that right triangle is the angle here at Y. All right, so far we have two really important right triangles. This one, and then also AFD as well. Now there's going to be a third important right triangle. I'm going to construct this horizontal line here from F to H. And I have a triangle here, DHF, that is also a right triangle. And one of the important things about this right triangle is we happen to know that this angle up here is congruent to this angle down here. And we know that just because HF and AG, these are parallel lines. And so the measure of this angle is going to be complementary to the measure of this angle right here. And so the complement of that, which is the angle up here, is going to be equal to this original. So we're seeing the angle that we're calling x appear in two different spots. And so in total, well, actually, let me say one more thing. We have a fourth right triangle that's important here, and that's the triangle AGF. One of its angles is x, and the rest of the angles, we don't really know what their measures are other than this right angle over here. So there's four right triangles that I'm interested in. AED, in which one of its angles is x plus y down here, and its hypotenuse is equal to 1. We have AFD, where one of its angles is y, and its hypotenuse is also 1. That's super helpful. DHF, where we don't really know any of the lengths yet, but we do know one of its angles is equal to x. And then also AGF, where again we don't know any of its lengths, but we do know that one of its angles is equal to x. So this is one figure where there's a lot of stuff going on. And because of that, we're going to be able to get a lot of mileage out of this figure in order to figure out how the trigonometric ratios, the sines and cosines, are going to be related one to another in this diagram. So let me try and arrange this so we can see the whole screen. So what I did on this diagram next is I just went through it with a SOHCAHTOA comb, a fine-tooth SOHCAHTOA comb, and asked myself, what all information can I get out of these four right triangles that we're interested in? So starting from the right triangle AED, this one right here, it's got an angle of x plus y in it. And according to SOHCAHTOA, the sine of x plus y is going to be the length of the opposite side, so that's DE here, divided by the length of the hypotenuse, which is 1. So I find out that the sine of x plus y is the length that we're calling DE in this diagram. Similarly, the cosine of x plus y is the adjacent, which is AE, divided by the hypotenuse, which is 1. So the sine and the cosine of x plus y we get directly out of this first right triangle, and I get the first two observations that I have down here at the bottom of my list. Okay, what about the triangle AFD? That goes from here to there to there. This is a right triangle by construction. This angle down here is the angle we call y. What do we know about it? Well, the hypotenuse of this right triangle is also 1, which is super helpful, right? Because then that means that the sine of y is the opposite side, df, divided by the hypotenuse, which is 1. So the sine of y is equal to df. And the cosine of y is the adjacent length, af, divided by the hypotenuse, which is 1. So the cosine of y is af. So those two triangles give me these four equations just from the sine and the cosine in SOHCAHTOA. Now my remaining two triangles both have something in common because they both have the angle x included in them. Let's take a look first at the triangle AGF, the one that we have right here. The sine of x is going to be the opposite side, FG, divided by the length of the hypotenuse, which is AF. I don't know what either of those lengths are, but I know that the sine of x is going to be the ratio thereof. Similarly, the cosine of x is going to be AG divided by AF from that triangle. Okay, again, SOHCAHTOA. Then from my fourth important triangle up here, the sine of x is the opposite side, which is FH, divided by the hypotenuse, which is now DF. And the cosine is DH divided by DF. Okay. So all I've done is I drew this diagram, I identified four right triangles within it, and for each one of those right triangles I asked which one of these angles do I know the measure of, and depending on the triangle it was either x, it was y, or it was x plus y. And then what does SOHCAHTOA tell me are going to be the sine and the cosine of the angle that I know inside of each one of those four important right triangles. So I have these 8 different observations, and I know now by definition of sine and cosine in right triangles that all 8 of these things are true. Now here's where the magic happens. I want to make 2 more observations about lengths. Because FH and AC are both horizontal in this picture, they're parallel to one another, I know for sure that if I added together FH up here with AE from down here, that I'm going to get the same thing, the same length, as if I added if I added GE to EA. So this length here, FH, is congruent to this length here, EG. In fact, this is a rectangle, and that's the reason why, right? And so if I add FH and AE, I'm going to get AG, right? This whole horizontal length here from the center of the circle out to this point at G. And for the same reason, because this is a rectangle, FG is congruent to HE. And so if I added FG and DH together, I would get the same thing as if I went straight from D to E the whole way. So these two are both just expressing the fact that the lengths AG and DE can be found by splitting them up into 2 and adding them into these lengths that we already know something else about. So this is all the information that we're going to need to get to where we're going. So now let's make the magic happen. I want to take my first equation right here. DH plus FG is equal to DE, right? So this vertical length added to that vertical length is equal to this full vertical length from D to E. What can I do with that observation? Well, DE, looking over here in my list, DE is something that I know by another name. I know it as the sine of x plus y. So let's just substitute sine of x plus y in for the length DE. No sweat, right? But what about DH and FG? What can we say about those? We have some information from up here. For example, we can say that the only place that we have an FG up here from anywhere is right here. FG divided by AF is equal to sine of x. So let's take the AF and multiply by AF on both sides, and then use that to substitute for FG. Sine of x times AF. My head's kind of in the way here. I'm going to slump a little bit. Okay, so we're making some progress, but now we have an AF that we don't otherwise know what to do with. So we look over in our chart again. Do we know anything about AF? Actually, we do. AF is another name for the cosine of y. So we'll put AF in there as the cosine of y. Now it really looks like we're making some progress. Now all we have is this unknown DH that's sitting out in the front. Do we know anything about DH? Looking down my list, the only thing I know about DH is from this equation. DH divided by DF is equal to the cosine of x. So I'll move the DF to the other side, multiply by it, and then substitute DH for the cosine of x times DF. Okay, but then what is DF? What do I know about it? The only thing I know about it is that it has another name, namely the sine of y. So when I substitute the sine of y in for DF, we have now eliminated all of our unknown lengths from this formula, and we've gotten, let me just shrink this down a little bit so we can see the whole thing in all of its glory. We've gotten a formula that we call the addition formula for sine. It tells me how to determine what the sine of the sum of 2 angles, x plus y, is based on nothing more than the sine and the cosine of the original angles, the original addends themselves, x and y. Right? So this is our first big important addition formula for sine of a sum of two angles. Let's play the same game just with this other equation down here and see if we can get another similarly happy result. Well, let's again start with the cosine of x plus y, this AE. That's something that we already know by another name, so we'll substitute. Instead of AE, we have the cosine of x plus y sitting right there. All right, what else do we have? I've got an FH, and to figure out FH, the only place I can go is to this equation. FH is nothing more than the sine of x times df. So I'll make that substitution. There we go. But then we have to ask, well, what's df? df is the sine of y. And so in we substitute, and we're making progress. What about AG? Well, it's this last equation that I haven't done anything with yet. Multiply by AF on both sides. Substitute. AG is the cosine of x times AF. But what is AF? AF is the cosine of y. In it goes. And we've eliminated all of our unknown lengths. So now I have this equation. Cosine of x plus y added to the product of the sines of x and y is equal to the product of the cosines of x and y. If I want to use this as a formula, probably the thing that I'm trying to use it for is to determine the cosine of the sum. So I want to get that term by itself. So I'll take this sine of x times sine of y, and I will just subtract it from both sides. I'll just slide it over here. And now we have the infamous formula that we call the addition formula for cosine. So the cosine of x plus y is the difference, cosine of x times cosine of y minus the sine of x times the sine of y. So these are the two formulas that we call the addition formulas for sine and cosine. But this isn't exactly what I sort of was promising here, right? What I was promising was a double angle formula, something which can tell me the sine of 2x and the cosine of 2x. Well, we can deduce those formulas from the formulas that we just got down here. All we have to do is take x and y to be equal to one another, to be the same angle. Because then x plus y is another name for 2x. So I'm just going to write down here in my palette here, x and y, if we take them to be the same, we're going to use that as the magic here. So if x is the same thing as y, then we'll just replace my y's by x's. And take a look at what happens. X plus x is going to give me 2x. And on the left-hand side, I've got cosine of x times sine of x plus the sine of x times the cosine of x. Those two are exactly the same as one another. Sine times cosine, cosine times sine. Multiplication is commutative. So those are like terms. And when I add them together, is it going to let me do it? Let's try it. If I factor sine x out of both of these terms. Ooh, maybe it'll let me do it now. Yeah. We get 2 times the cosine times the sine. And this is the famous formula that we call the double angle formula for sine. The sine of 2x is nothing more than twice the sine of x times the cosine of x. Nothing to it. Same thing happens if we look for a double angle formula for cosine by replacing its y's by x's. I'm going to get cosine of x times cosine of x minus the sine of x times the sine of x. It's not quite as friendly of a formula, but we can rewrite it in terms of squares. Cosine squared of x minus sine squared of x. And this, whoops, combine these x's together inside of my cosine. This gives me the double angle formula for cosine. Right? And by the way, one of the things that you might notice, and this will be my last comment for the work that we're doing here. This has been kind of a theoretical day, so thank you for hanging through all of this. One of the things that you notice, that I notice, is the similarity between the Pythagorean identity and the double angle formula for cosine. Right? On the one hand, the double angle formula for cosine says that the cosine of 2x is the difference of cosine squared minus sine squared. On the other hand, Pythagoras says that 1 is equal to the sum of the cosine squared with the sine squared. And it turns out that we can do a lot by combining these two equations together to, for example, get a reduction formula. Let's see if it's going to let me do this. I don't know if it's going to let me do this. Probably not. But we can combine these two equations together to get more identities as well. But if you're looking for double angles, you can look no further than the two that we have listed down here. And so this is kind of a summary. This will be where we wrap this up today, of what I consider to be the three most important trigonometric identities. Double angle for sine, double angle for cosine, and the Pythagorean identity. With the Pythagorean identity being the one which is easily the most significant of all three of them. But these are the three what I think are the most important to know in all of trigonometry. So that's where we're going to wrap up today, and thereby also wrap up the new material exposition for the semester. Beginning with next week, we're going to be focusing on just assessment and feedback. So working through quizzes, working through practice problems, working through the web work, working through exams. And so I may still do some occasional live stream meetings. I'm going to hold this time on Mondays and Wednesdays to be available for that. But I want to be responsive to the questions that you have. So if you have questions on the work that you're working through, please drop them to me in a message via Canvas or via email, and I'll try and respond to those questions directly during these times as well. I'll also be sharing out any sort of hints or tips or tricks that I might have on the work that you're working on that can help you to make that progress. Be in communication with me, because that's what these videos are going to turn into for the rest of the semester. So I look forward to that. I hope you enjoyed, if you watched through a lot of these videos, I hope that you enjoyed some of the presentations and the content. This is going to be, though, where the new material for this semester wraps up. So I hope you enjoyed it, and I will see you on the tubes.